Quantum numbers. Quantum numbers are going to be like an address for an electron. Remember, they're going to be solved by using the wave equation. The first quantum number we're going to look at is n. N is the principal quantum number. And if you notice, we've kind of talked a little bit about n. This is your energy level, which is also known as a shell. And we'll talk about this one next. The second quantum number is L. L is the angular momentum quantum number, and it gives us the shape of the orbital. So if it's a circle, if it's kind of a balloon-shaped dumbbell look to it. So the shape of the orbital, and we call this subshells. M sub L gives the magnetic quantum number, and it's the spatial orientation of the orbital. So that tells us if it's going to be up and down, left to right, things like that. And then the fourth one is M sub S. This is the electron spin quantum number, but this one is not derived from the wave function. It tells us the spin of the electron. Okay, so only the first three here are derived from the wave equation. The fourth quantum number, the electron spin quantum number, is not derived from the wave equation. So let's talk about these four quantum numbers. The first one, n, which is the principal quantum number. Okay, here we have our picture of our atom, and this looks a lot like Niels Bohr's model. So Bohr's model was actually fairly good, but there were some downsides to it. In order to explain n, we're going to use Bohr's model because it does do a pretty nice job with it. So electrons in an atom are grouped around the nucleus into shells. Okay, so where is the nucleus in this atom? Right in the center, right? So you have your nucleus right in the middle. And it says that electrons in an atom are grouped around the nucleus called shells. So you have some electrons in the first shell, n equals 1. You have some electrons in n equals 2, and so forth. The farther a shell is from the nucleus, the larger it is. Okay, that hopefully should make sense because if you look at n equals 1, n equals 1 is fairly small. Now, let's say you look at n equals 3. N equals 3 is going to be a lot bigger. Okay, now because n equals 3 is bigger, you can hold more electrons. So if n equals 1, that's fairly small, so it can't hold as many. N equals 3 is bigger, so it can hold more. Okay, and then the higher the energies of those electrons, the further it is from the nucleus. So with n equals 3, well, let's start at the below. N equals 1, it's going to have very low energy. With n equals 3, you're going to have higher energy. You can kind of think of this as a how tall a building is. So for n equals 1, that's like a first-story building. With n equals 3, that's a third-story building. So if you have an electron, for example, going from n equals 3 to n equals 1, that's quite a bit of a jump, right? If instead they went from n equals 2 to n equals 1, that's not as much of a jump. So you have high energy when you have a big jump, low energy when you do a small jump. Now the first shell, n equals 1, is closest to the nucleus, and it can hold only 2 electrons. Now, the second shell can hold a total of 8 electrons, And then the third shell can hold a total of 18 electrons. But how do they get 2 electrons? How do they know that the second shell holds 8 and the third shell holds 18? This is actually really interesting in my opinion. We're going to learn about the organization of an atom through these quantum numbers. Okay, so the first quantum number, just as a review, are known as shells. Those are n equals 1, n equals 2, that kind of thing. The second quantum number is L. L is the angular momentum quantum number. The letter L, so this is kind of confusing when you're trying to read this. L is not 1. So when you are looking at quantum numbers, because L and 1 look exactly the same sometimes, you have to be really careful. So here, this is the letter L. Okay, so the letter L describes the shape of an orbital, which is the volume an electron will occupy. This is the most probable area an electron will be found. Okay, remember, it's the probability. The reason why is because electrons will not go in a defined path. You can only find the probability of where an electron will more likely be found. And you do that by taking the wave function and you square it. The letter L can have any integral from 0 to n minus 1. What does n represent? N is that quantum number, so n is your shell. Or you can also say energy level. They're synonymous. Okay, so L can have any value between 0 and n minus 1. Orbitals within a shell are grouped as subshells according to the quantum number L. Okay, so we said that n is our shell, so L is our subshell. And different subshells are usually designated by letters. We can have S, P, D, and F. Historically, the letters came from the words sharp, so S for sharp, principal for P, diffuse for D, and fundamental for F. And it describes various line spectra. You don't need to know that. You just really need to know what the subshell letters are designated as, S, P, D, and F. After F, successive subshells are designated alphabetically, so G, H, and so on. But the ones that are more common that we will use in chemistry is S, P, D, and F. The reason why is because all of the atoms on the periodic table will use these 4 main subshells. Now that we've talked a little bit about L, let's really understand what L is and how to find it. Let's do that by filling in this table. So the top row tells us the quantum number n, which is your shell. So you have n equals 1, n equals 2, n equals 3, and so forth. Now remember, L can have any values between 0 and n minus 1. So if I look at if n equals 1, what would L have to be? The only value that it could have is 0. Okay, now if I was looking at 2, or sorry, let me back up. Staying with if L equals 0, the subshell notation of that would be S. Okay, now if n equals 2, L can have any values of 0 or 1. We know that 0 will be an S subshell, but if it's a 1, that corresponds to the next subshell, which is going to be P. Okay. Okay. Now for n equals 3, because L can have any values between 0 and n minus 1, it could have the value of 0, 1, or it could have 2, because 3 minus 1 would be 2. We know 0 corresponds to S. We know 1 corresponds to P. And 2, that's going to correspond to the next subshell, which is known as D. And the fourth one, if n equals 4, the quantum numbers could have any values between 0, 1, 2, and 3. So we know 0 corresponds to S, 1 corresponds to P, 2 corresponds to D, and finally the third corresponds to F. Now, if we remember, the L describes the shape of the orbital, and the shape is the most probable area for finding an electron. So for example, this is an S orbital, and if you look, you see all these little dots on there. Those dots mean the most probable area that an electron will be found. It's kind of like it's a probability map. Now, what we can do is we can kind of smooth out these kind of rough patches in a sense, and we can get like these smooth shapes. So the S orbital is basically a sphere. And so they look at the probability map and they just kind of make the most probable area that an electron will be found. So an electron will be found most probably in this area. So an electron will be found most probably in this volume. Okay, now the p orbital is going to look kind of like a dumbbell shaped. The d orbital, most of them will have this clover leaf shape, and an f orbital, f's are just really weird shaped. Later on in the notes, we're going to look at how they actually got these shapes, but for right now, don't worry about it. You need to be fairly you have to kind of know these shapes. You don't need to draw them per se, at least some of them, but you need to be able to recognize. So an s orbital is the simplest one to recognize. It's a sphere. Okay, the next one is a p orbital, and so that only has, it's called 2 lobes, 2 sides, 2 circles. And then you have the d orbital. Here you have 4 lobes, and then an f orbital you have, at least in this one, you have 6. Now let's talk about the third quantum number. The third quantum number is m of L, and it's known as the magnetic quantum number. Okay, now another thing to note is that L, right here, it looks like a 1, but it's actually the letter L. So the quantum number m of L gives the spatial orientation of the orbital. So it tells us if it's up and down, left to right, that kind of thing. M of L can have a little bit more values than L. It's going to have any value between negative L to positive L. And again, it's that quantum number L. It's not a 1. Now let's fill in this table to help us kind of understand m of L. Here we are given L. L is denotes the subshell. So if L equals 0, what would our subshell be? The subshell notation is going to be the letter. If L equals 0, that's going to be an S subshell. Okay, that's something that you need to know. If we have the subshell notation of S and L equals 0, what would the quantum number m of L be? Well, it can have any value between negative L to positive L. So if L is 0, negative 0 to positive 0, that's the same thing, right? So it's just going to be 0. Okay, now let's fill in these blanks. Because I only have one number of m sub l, I only have a 0, I can only have one orientation of the s subshell. So if you look at the s orbital, so you have your axis here. Your s subshell can only have one orientation. It's only going to be a sphere. Now let's look at the next one. If L equals 1, what is the subshell notation? This means a P. Again, that's something that you need to know, you need to memorize. Now we need to figure out m sub L. Now m sub L can have any value between negative L to positive L. Our L in this case is 1. So it can have any values between negative 1 to positive 1. So negative 1, 0, and plus 1. Now let's fill in this part. How many m sub L values do I have? I have 3 of them. So that means I can have 3 orientations. Okay, so I have 3 orientations of the P subshell. Now this is going to be kind of a hard drawing, but let's say I have my axis here. So I can label, let's say, Z, X, and Y. A P subshell, we haven't talked about this at all yet, but the P subshell is going to look like a dumbbell. And so one orientation will be along the Z axis. So I can say this is P of Z. Another orientation I can have, so if I draw out my Cartesian plane here, label my axis. Instead of it being on the Z-axis, where could it go? Well, it could go, let's say, on the X-axis. And so I would label this as P of X. And then the third one, draw out my axis here, and label it Z, X, and Y. The third one could go along the other axis, which was Y. And we would label that as P of Y. So notice how we have 3 orientations that we can have. Now let's look at the next one. Here we have L equals 2. If L equals 2, what is the subshell notation? This is going to be the D subshell. Okay, and then what are the quantum numbers that this could have? And I should say the quantum number m sub L. What could that have? Well, because it can have any values between negative L to positive L. In our case, it's 2. It can have any values from negative 2 to positive 2. So that would include negative 1, 0, 1, and 2. Okay, now how many orientations could the D subshell have? Because I have 5 values of m sub L, I can have 5 orientations of the D subshell. And D subshell is a lot harder to draw, so I'm not even going to draw it here. I'm going to wait to show you a picture of it. But I can have 5 orientations of the D subshell. And then the last one. If we have L equals 3, what is the subshell notation of that? This is F. Again, that's one of those that you need to memorize. What would the quantum numbers, what I should say, what are the m sub l quantum numbers I could have? Any values between -3 to +3. Okay, so then how many orientations could I have? This will give me 7 orientations because there's 7 numbers. And so there are 7 orientations of the F subshell. Now, if I try to draw the F subshells, it would be a very sad day because those are insanely hard to draw. So the S subshell, very easy to draw, and as you move up, they get a lot tougher. The last quantum number we're going to look at is m sub s. So this is our 4th quantum number. So the quantum number m sub s describes the angular momentum of an electron. That's just fancy to describe the way it spins. It is not solved through the wave equation. Okay, so you don't need to figure out what psi is. So you don't need that. Electrons can spin in 2 ways. One of those ways is clockwise. So clockwise we denote it as +1/2. Okay, now we denote electrons as these half arrows. So I can say if electrons are going clockwise, I can put 1 in the up direction. What would be the opposite of clockwise? Counterclockwise. And with this, I mean, the electron is just spinning in the opposite direction, spinning counterclockwise. So we denote that with a -1/2. I can denote it with an arrow by putting it in the down direction. So m sub s will only have 2 values, +1/2 or -1/2.